Okay, so now once we have understood what the first law of thermodynamics means, let's go into some of the special cases which will be very interesting. Okay, so we know that the first law of thermodynamics is this: dE is equal to del Q minus del W. And what's the convention that we have used is expansion is positive. Why is expansion positive? Because during expansion, your force is applied and the displacement is in the same direction as the force applied. So F dot dx becomes a positive number, therefore expansion, which is the work done during expansion, becomes positive. So when we have this convention, this is the first law of thermodynamics, okay? So we have to keep in mind the convention, the sign convention that we are using when we do this. Okay, so for expansion, we have assumed that this is a positive, this is positive. Okay, now when do we have the change in internal energy as positive? Okay, so if the supplied heat becomes like 10 joule, right, and you use those 10 joules, you use 2 joules out of those to expand, then what will be the dE? That will be 10 minus 2, which is 8. So 8 joules is greater than 0, right? And therefore the internal energy increases. Okay. Now this is very simple. Like it is greater than 0, internal energy increases, and vice versa. Like when you have when the dE decreases below 0, the internal energy drops. Now why will this happen? Now let's assume that you had $100 and you spent $20 out of that to $20 to roam around, to go on a trip. Now, the remaining goes into the internal energy. The remaining goes into your savings account, right? Now, let's suppose you don't have an external income, and you still want to go a trip, or you gain $100, you profit $100, but you spend $150 for going on a trip, right? So you are running short, you have to get $50 from your savings account. Now this internal energy will be your savings account in this case. Now internal energy will be reduced if you do an expansion more than what the energy you gain. So in that case, the dE will be less than 0 and the internal energy will come down, will be reduced. Okay. Now when delta Q is 0, delta Q is greater than 0, means that the body is gaining heat. Now remember, when we were discussing about the exothermic and the endothermic relationships, we saw that when the body gains heat from outside, we call it an endothermic process because the heat is coming in, endothermic. So therefore, delta Q becomes greater than 0. Like that's why we have a positive sign in an endothermic, because the delta Q is 0. The reverse is true for an exothermic process. When the body loses heat to the surrounding, the delta Q becomes negative, and that's why you have a negative sign in an exothermic process, because the delta Q drops. Okay? Now, very simple case, when you do not have any heat exchange with the body, like you have an insulator condition in which the heat is not being exchanged from the system to the surrounding. In that case, the delta Q, the del Q will be 0. There is no heat exchange. In that case, what does this equation become? This equation becomes dE is equal to minus dW. That kind of a process is called an adiabatic process, right? Because there is no heat exchange. It's just a name. It's just another term that is coming in to say that when delta Q is 0, that process is called adiabatic process. In an adiabatic process, this will hold true, that dE will be a negative or delta of the work done. So if you're not earning any money, right, you're earning $0, but you still want to spend $100 for doing some work, for doing some expansion, right? You spend $100 here. So what will be your savings account? It will go down by $100. It's the same explained as here, right? Okay. Now, when you have del W is greater than 0, it's an expansion, as we saw, because the force and the displacement are in the same direction. We have expansion, and that's why we have delta W is greater than 0. This you have to understand this as the system does work on the surrounding. Now, You have the piston, you have the gases inside, and the gases are trying to force the piston out, right? So the system, the gases make up the system, they are doing work on the system. Now, if the gases are successful in pushing, that will be expansion. Now, when you're doing expansion, the system will lose its energy, right? So that is system doing work on the surroundings. So the system, in the gases inside are doing work on the system because I'm losing energy, right? I'm doing some forcing and I'm doing some positive work when the system is doing work on the surrounding, right? Now, people get confused when they see the chemists using a different idea of expansion and the different signs of expansion and the different signs of and therefore they are using slightly different variations of the first law of thermodynamics. It's very simple. What we saw in here was dE is delta Q, del Q minus del W, because we had expansion as positive. Now this will be true for everywhere in the universe, right? Just because I change the system will not change the law itself, just because I change the convention. Now, what if I say, let me take that expansion is negative. Let me just assume that expansion is negative. Now, why would you do that? This is what chemists did. Why? Because they said that when you are doing work on the system, during an expansion, you are doing work, so you are losing that energy. They said that, okay, since you are losing energy, let's call that expansion negative. So what they did, they reversed the convention. They said that if we are having expansion, we will consider that work as negative. Now, when you have a negative work, we still know that this law will still hold true. But what they did, they just changed this sign. Now, this whole thing has a changed convention in here. We just changed the sign in the equation. Now let's take an example. Now we know that if you have 10 joules of heat coming from outside and you spend that 10 joules, out of that you spend 4 joules in doing some work, you know that your internal energy will be 10 minus 4, 6 joules, right? Your internal energy will change by 6 joules. Now, the physicists did it here. They said that delta W was positive. So 10 minus 4 became 6 and you got 6. No problem there. Now here what the chemists said, that okay, I know that when we are doing an expansion, they said that we are doing some negative work. So they already have a negative 4 in here. So what they did was, you know that we had 10 joules in here, and you said that, okay, I'm doing expansion, but instead of saying 4, what they did, you said minus 4. So that's why this plus should be here. So that this minus sign is taken care of inside this equation. Because of this convention, we just changed the sign in here. That is the only difference between physics and chemistry, the sign conventions. The heat sign convention are same for both physics and chemistry. But generally, expansion is considered positive in physics, and that's why you have this law. And since if you consider expansion as negative, you will have this law. Because you cannot just do it again, right? You have to take care of the signs. Okay, so since there is a negative already, you don't want it to be like negative again, then the whole thing becomes problematic. So just to take care of this convention, the chemists came up with this idea, okay, just change this sign in here. You understand? So there is no difference between thermodynamics when physicists see it or chemists see it. Nature will behave the same. It's just that the sign conventions are different. Why? Because expansion is negative in here. Okay? It's a very simple concept actually. Please understand this and never get confused again. Okay? Now, let's understand what internal energy is. Now, as we said that internal energy is a state function which does not depend on the path. It's path independent. Now, if we see a similar diagram that we saw in our first video, that we have a P and a V, if we want to find out if A is the initial state and B is the final, the internal energy change in path 1 will be exactly equal to path 2. Why? Because in both these cases, the internal energy change will be EB minus EA. It won't matter which path you took. So that's why internal energy is a state function. Since it's a state function, it's also a perfect differential, right? It's a perfect differential because we saw earlier that all state functions will be perfect differentials. Now, since this holds true, the state function the internal energy is a state function. Now, if you have a process, if you have a state A and this goes to state B and goes to state C and D and then again comes back to its original position. Now, since it came back to its original position from where it started, the internal energy change would be 0 because the final is equal to initial, right? So that is represented in here because when you go in a loop, any kind of loop, the shape of the loop does not matter. If you go in any kind of loop and you come back to the same, then dE will be 0. Why? Because this is a state function. This will not change. That's why in a state function, if you go in a loop, this becomes 0. Okay? But the story is entirely different when you have work and heat. Now, I say that they are path dependent. Now, you don't have to believe me. Let's find out how it is path dependent. Now, you have to understand this, that work is P delta V, right? We know that like work is represented by this, like pressure into the volume, because you have some pressure going on in here. Now, if you expand, if there is a delta V, if there is an expansion, then you are doing positive work. So, okay, I will not be following this this law. I will be following this one because it's more easier to interpret, right? Because expansion is positive because force and the displacement are in the same direction, positive. So we will be following this version of the first law of thermodynamics. So in here you have certain volume in this piston. Now you have some expansion. So there is some delta V. So because of this delta V, you have a positive delta V in here. So the work done will be positive. So the opposite will be true in here. Since the delta V is negative, the work done will be negative. Okay. So work done is pressure in P del V. Okay. Now, why pressure is P del V? You might already know, but if not, we'll be dealing with it in a slightly different lecture. Why work is P delta V? It's very simple derivation. Okay. Okay. Now, if you have this closed function when you are moving from A, B, C and D, okay, now we already know that this is a closed loop. So when you are moving from A to B, then to C, then D and back to A, the delta E of the entire cycle will be 0. Why? Because E energy is a state function. When you come back to the same position, the delta E is 0. But what about work? Okay, let's find out. Let's find out what happens when state A changes to B. What is the work when work done when the system changes from A to B? Now the work done will be delta W1 and you integrate it from A to B to find out the total work done when you are moving from point A to point B. This will give you W1, say this is path 1, this is W1, this is path 2, 3 and 4. So W1, 2, 3 and 4 respectively. Now what you get is P delta V integrated from VA to VB. Okay. Now when you have VA to VB, you see that the volume is getting decreased, right? So you had some higher volume, now you have some lower volume, right? So in this case the work done will be negative. Whatever the amount of work is, the amount of work, the sign of the work will be negative because you are doing a contraction there, a compression. Okay. Now this integral sign tells you the mathematics is the integration from A to B. What physically means is the area under the curve. So whatever the shaded portion is will give you, if you find out just the area between this shaded portion, this will give you the magnitude of work done when the state changes from A to B. The sign will be determined by the sign of delta V, and that's why we have a negative in here because the delta V is negative. So we know that the amount of work done is the magnitude of the shaded area and has a sign of negative. Let's assume this is negative 100. Okay. Now, moving on, the work done at path 2, like W2 and W4, are termed 0. Why? Because there is no change in volume. They all stay the same. When you change from state B to C, there is no change in volume. And when there is no change of volume, that means the gases keep on pressurizing this, but the volume of this whole thing is not changing. This whole piston is not moving. So since the piston is not moving, that means that there is no volume change, and when there is no volume change, there is no work done by the gases. So there is no work done, so there is work done is equal to 0, because the delta V is equal to 0. This is true for W2 in here and W4 in here, because you see, when you move from B to A, the volume remains the same. Pressure drops, but the volume remains the same. In here, the pressure increases, but the volume remains the same. That's why W2 and W4, the work done is 0, because delta V is equal to 0. Now, interesting thing happens when you come from C to D, is the same thing. You do a P delta V from C to D. Like you do a P del V from C to D. Like you integrate P delta V through this path. Now, how do you get what is that answer? The area that is shaded, like these red dots, everything that is below this, that area is the magnitude of that work. Okay? That is the magnitude of work. Now tell me the sign of that. The sign will be positive. Why? Because you have a VC which goes to VD. Now the sign is you have a lower volume and you are going to higher volume. So you have a lower volume, you are going to higher volume. So you are expanding. Expansion means delta V is positive. Delta means positive. That means you are doing positive work, right? The force and the displacement in the same direction. Expansion, positive work, right? So whatever that area is, say 150. So that plus 150 will be the area of this whole thing. Now, what is the total work done when you move from A to B to C to D and then back to A? The summation of W1 plus W2 plus W3 plus W4. This was minus 100, right? From A to B. This was 0, this was 0, this was plus 150. Because clearly, this work is more than this. Whatever that is, just taking an example that it is 150. It has to be more than that, because you can see visually this is more, right? So when you add them all, you are getting a positive number, right? Which is not equal to 0. That means work done was not 0 in this whole cycle. Delta E was 0 because you came back to the same point. But work was not equal to 0. And since work was not equal to 0, Q cannot be equal to 0, because if you have delta equal to 0, if you rearrange this, del Q will be equal to del W. Right? That's why we have written here. Q of the cycle will be exactly equal to the work of the cycle. So, in here we learn that when you go around a path, delta E becomes 0, but delta, like Q of the cycle and W of the cycle are not 0. And they are equal, because of this simple mathematical equation, right? So I hope this is clear.